And welcome back to the Aero Guy, your source for in-depth discussions on aviation concepts and principles. For today's video, we'll focus on the derivation of equations used for the standard atmosphere. These equations define how pressure, temperature, and density change with altitude, forming the foundation for aircraft performance, flight planning, and aerodynamic analysis. When we conducted data gathering for atmospheric properties, we noticed something interesting. While density and pressure follows predictable trends with altitude, as altitude increases, pressure decreases. As altitude increases, density also decreases exponentially. However, temperature behaves differently. This is mainly brought about by factors like weather patterns, solar radiation, and local atmospheric conditions. Observing closely the trend for temperature with altitude, you notice that temperature decreases with altitude at a constant rate. That's from 0 to roughly 11 kilometers. Then onwards, from around 11 kilometers to about 20 kilometers, the temperature remains at a constant value. Then onwards, it increases at a constant rate again. Now let's take a look at the overall trend of temperature with altitude. If you analyze the standard atmosphere, you'll notice a distinct pattern with temperature change as altitude changes. At sea level, again, temperature decreases as altitude increases. At around 11 kilometers, temperature becomes constant and remains steady for some distance. Now beyond this point, temperature starts to increase again, pauses, and then decreases, and then pauses, and then at the last layer, it increases even further. Now we will not discuss the reasons for these temperature changes in this video, as that's another rabbit hole to dive into, but maybe for another time. But just a quick introduction. The significant temperature changes defines each layer of the atmosphere. And each pause in such significant change defines a transition from one layer to another. With this understanding, the unpredictability of temperature with altitude becomes slightly predictable by breaking the atmosphere into layers. Based on temperature behavior, we can define standard values of temperature with altitude, which serve as the foundation for modeling the atmosphere in aviation and aerodynamics. So let's continue working with temperature as it changes with altitude to define an equation for our modeling of the atmosphere. Let's look at this graph. This is a breakdown of the same graph we presented earlier, but this time we included the temperature changes with altitude for each layer. In the first layer, we define it as the troposphere at 0 to 11 kilometers. This is the rate of change of temperature with altitude. And again, at the pause, we call it the tropopause. There is no change of temperature with altitude. And after the tropopause, there is an increase of temperature with altitude, and the rate of that change is given by this value. And with that, we may be able to use such trends to define the standard temperature for our standard atmosphere. However, we cannot use this graph as it is presenting data in a way where altitude changes per temperature change. Instead, we need to interchange the axes to better visualize how temperature varies with altitude. So, by setting the y-axis as temperature and the x-axis as altitude, we restructure the graph to clearly show how temperature behaves at different altitudes, making it easier to interpret and apply in our atmospheric modeling. So now let us derive an equation to express how temperature changes with altitude. for modeling the atmosphere. We will be utilizing this visualization of temperature change with altitude, but I've included this graph just to get the trend of how temperature changes with altitude for each layer. But for our derivation, we will be only deriving or starting at the first layer, which is the troposphere. And then later, we'll look into deriving an equation for the tropopause. Okay, so to start that, let us break down or let us simplify this graph, this part of the graph, for our analysis. Allow me to write down another graph. And that's express temperature in terms of Kelvin for engineering calculations. Again, in the troposphere, as we increase the altitude, temperature decreases. So the trend would look like this one. At sea level, temperature decreases with altitude to a certain value. Okay, so we basically created a line with 2 points. And with that line, our analysis for temperature and altitude can be simplified using basic algebra. In particular, we will be able to use the equations of a line. And to be specific, this equation. Why? Simply because temperature varies linearly with altitude. And if we know 2 points along this line, any 2 points along this line, we may be able to define each point, each temperature with altitude at the standard atmosphere and at the tropopause. And good thing, we gathered enough data to determine the temperature at sea level and at 11 kilometers. Now, what are these temperatures again? At sea level, the temperature is at 288.16 Kelvin. That's roughly 15 degrees Celsius. And at 11 kilometers, the temperature is at 216.66 Kelvin. Convert it to Celsius yourself. Now, let's define those points. At sea level, at 0 kilometers, the temperature is 288.16 Kelvin. And at 11 kilometers, the temperature is 216.66 Kelvin. Okay, so we basically defined 2 points along our line, and we will use such data to determine an equation for temperature variation with altitude. Again, the general equation to use is just an equation of a line. And we have defined y2. We also have y1. M is our slope. We have x2. And we have x1. Let us try to define the slope in this point. The slope is just the change in rise over the change in run. Basically, it's a difference between y2 and y1 divided by x2 minus x1. Do we have that data? Yes, we do. So we can solve for the slope. So the general equation is y is our temperature, that's temperature 2 minus temperature 1 equals the slope minus multiplied by the altitude, that's height 2 minus height 1. Now I'd like to change this slope into a more appropriate symbol. We use the symbol lambda, or we can use A by convention to define the slope. Okay, we also have a name for such slope. We call it the temperature lapse rate. The slope defines the trend, and the temperature lapse rate defines the trend by how much does the temperature change with a change in altitude. So since we have values for y2 and y1 and x2 and x1, we can figure out the value for the lapse rate. So how do you compute for that? The lapse rate is equal to y2 minus y1 over x2 minus x1. The lapse rate is now, what is y2? y2 is 216.66 Kelvin minus 288.16 Kelvin. What is x2? x2 is your 11,000 meters or 11 kilometers minus 0 meters or 0 kilometers, because we are starting at sea level. Now, let us input the data in our calculators. We get the lapse rate y2 minus y1 over x2 minus x1. That's 216.66 as our y2. y1 is 288.16, and 11,000 minus 0, that's just 11,000 meters. We get a value of negative 0.0065. And there you have it. That's your temperature lapse rate. That's negative 0.0065 Kelvin per meters. And you can convert this to appropriate unit as needed. Again, let me write that down. That's temperature 2 minus temperature 1 gives us the lapse rate multiplied by height 2 minus height 1. This is now your equation for temperature variation with altitude. And again, the lapse rate value is negative 0.0065 Kelvin per meter. So this equation is highly useful, as again, this makes the computation for temperature change with altitude predictable. With this equation, you may be able to figure out what is the temperature at a certain altitude. Let's say you were asked for the temperature at 3 kilometers. Just substitute the knowns. You know the temperature. You know the altitude to be at 3 kilometers. And you're looking for the temperature. Since you have 2 points along a line, just use this final equation. T2 minus T1, you're looking for the new temperature. You already know your sea level temperature. You already know your lapse rate. And you know the height that you're comparing. And now let's move on to another property that describes the atmosphere. You have the pressure. Unlike your temperature, pressure is relatively straightforward. There is an exponential decrease of pressure with altitude, and we've already started to derive a general equation for pressure change with altitude through the hydrostatic equation that we derived in the first video. So with that, let me write down the hydrostatic equation considering geopotential altitude. Again, this equation relates the change in pressure with the change in altitude. So, how do we make this equation useful? We will be utilizing mathematical tricks by substitution, and eventually we'll go over some integration just to derive a usable equation. So without further ado, allow me to begin deriving by dividing both sides by P. And as we know, by equation of state, P is just density multiplied by the gas constant times the temperature. Substituting that, we get dP over P equals negative density gravity sea level times the dH divided by the density RT, canceling the two factors. You get dP over P equals GO dH over RT. And recall from our earlier derivation, recall that the lapse rate is equal to change in temperature over change in height. So we get, or we can substitute dH from the lapse rate to this equation. Continuing, allow me to copy that. We get, again, the lapse rate is dt over dH. dH is therefore dt over the lapse rate. Substitute that. dt over RT times the lapse rate. So now we get an equation that we can integrate. Allow me to rearrange the factors first. Lapse rate, gas constant times the temperature. Since we have a differential equation, let's make this whole by integration. We will now integrate the two sides of the equation. With the first side, the limits are from pressure 1 to pressure 2. And on the second side, on the other side, the limits are temperature 1 and temperature 2. So by integration, by rules of integration, we get ln P over P1 equals, since these three are constants, we let them out prior to integrating. Temperature 1, temperature 2. We get GO, lapse rate times R, ln T2 over T1. And to remove ln here, we exponentiate. And now we get to have a final equation describing the pressure change with altitude, described in terms of temperature change. This equation is what we call as the pressure ratio equation. And if you're interested on the steps of how we arrive from the equations above towards this equation, I have outlined the steps on this side of the screen. And as for density, again, from the previous video, density changes or decreases with altitude, similar to pressure. With that said, we can use the equation for pressure to derive an equation for density change with altitude. From the previous slide, we derived an equation for pressure change with altitude through temperature changes. And we'll do the same for density this time. By the equation of state, pressure is equal to density gas constant times temperature. Substitute this for both pressures. So we get density 2, R is a constant, temperature 2, divided by density 1, R is a constant, temperature 1, equal to T2 over T1, negative gravity at sea level, lapse rate times R. Cancel out similar factors. You're left with density 2 over density 1 multiplied by T2 T1 is equal to T2 over T1 raised to this factors. And transferring T2 T1 to the other side, we get density 2 over density 1 equals this term raised to this minus 1. And now you have an equation describing density changes with altitude through temperature changes. We call this equation as the density ratio. And now we have three equations already for temperature, pressure, and density for our modeling of the atmosphere. We can use such equations mainly in the troposphere, but let's try to apply the same derivation concepts that we used for the next layer of the atmosphere, which is our tropopause. So, just like what we did earlier for the troposphere, let's do the same for the tropopause. Let's analyze temperature, pressure, and density at the region in the atmosphere after the troposphere, which is the tropopause. So if you look at the tropopause, using the temperature versus altitude profile of Earth's atmosphere on the graph on the left side, again, they are the same graphs, but they are presented in a different manner. One is used for computation, and one is just used for visualization of the changes. So, look at the tropopause at 11 kilometers to 25 kilometers. At that region of the atmosphere, the temperature is a constant. Meaning to say, if you solve for the lapse rate, there is no change in temperature. Meaning to say, there is no equation required to compute for the temperature change with altitude. So what is the value of temperature at the tropopause anyway? The temperature at the tropopause is at 216.66 Kelvin. So now let's talk about pressure changes with altitude at the tropopause. Now, unlike your temperature, which remains constant at this region of the atmosphere, pressure does not do this at all. It maintains its decrease with altitude. And we cannot use the same equation as that of the troposphere, as those equations involve temperature changes. So this time, let us derive an equation that can be used for the tropopause. So, with that, we have the hydrostatic equation. Again, this describes the pressure change with altitude. We derived this in the previous video. And let us divide both sides of the equation by pressure. And substitute pressure on the right side of the equation by the equation of state. And here we cancel out the common variables and we continue. GO DH RT. Then we integrate this to make this equation whole and to make this equation usable. From pressure 1 to pressure 2, we exclude the constants in the integration process. Height 2, height 1. This will leave us with ln p 2 over p1 multiplied by height 2 minus height 1. And exponentiating, we get P2 over P1 equals e raised to the power of this factors. So now we have a final equation. This is the pressure ratio at the isothermal regions of the atmosphere. Now this can be used for aerodynamic calculations at the tropopause, but if you want to further model or derive a table for the ISA, you can use the same equation as well. Now talking about density, again, this behaves the same way as pressure does, and we cannot use the troposphere equations as temperature does not change at the tropopause. Hence, we need to derive a new equation. But we can start with, just like what we did in the derivation for the troposphere density equation, we can start with the pressure equation here. Okay, substituting for the equation of state, get density RT 2 and density 1 RT1 is equal to this term. Right. Now, since temperature does not change at the tropopause, T2 equals T1, you can cancel out these factors. Hence, you're left with density 2 over density 1 equals E raised to this term. There you have it. Density ratio for the isothermal regions of the atmosphere. Now that we've gone through the derivation of equations of how pressure, temperature, and density change with altitude, let's summarize what we've established. Again, these equations describe how atmospheric properties behave as altitude increases. We specifically derive them for the troposphere and the tropopause. However, these same equations can be used or can be applied to both gradient and isothermal regions of the atmosphere, making them useful beyond just the troposphere and the tropopause, making us or enabling us to model and to derive values for a standard atmosphere. And to help with the application of these equations, I've provided a table that defines different altitude names based on whether we're using temperature, pressure, or density to determine altitude. And this table will give you a clearer understanding of which equation to use in specific cases, as I've provided a column describing the purpose of that altitude. So for temperature, we call it temperature altitude. This is the altitude where a specific temperature occurs based on the standard atmosphere. This type of altitude is mainly used in meteorology and aircraft performance calculations. We also have density altitude that can be used for aircraft performance computation, affecting lift, engine power, and takeoff distance. And we also have pressure altitude. This is very common in aircraft manuals. This is also used for aircraft performance calculations and for flight level above the transition altitude. And now that we have a solid mathematical foundation of the changes to properties with altitude, we can explore how these equations are applied in real-world scenarios. I'd like to see you in the next video, and if you found this helpful, don't forget to like, subscribe, and share to support the channel and help more aviation students. Always remember, your attitude defines your heading, speed, and altitude. Thanks for watching, and keep learning.